Hello everyone, and welcome to the OxTS webinar on Boresight calibration. The webinar will be presented by Jacob Amacker, Product Engineer for the Survey and Mapping area here at OxTS. The first part of the webinar will be a presentation on Boresight calibration, what is it and why you need it. Then we will have a practical demonstrations on how to complete a Boresight procedure with OxTS Georeferencer software. And at the very end, we will have some time to answer any questions that you might have. So if you do have questions, please type them in the questions chat box in the GoToWebinar window, and we will try to get you an answer at the end. Thank you, and over to you, Jake.
Thanks, Sam. So, hello everybody. As Sam said, my name is Jacob. I am the Product Engineer for OxTS Survey and Mapping, and welcome to this webinar on the topic of our Boresight calibration solution. So we'd just like to open with a poll. So if you could tell us which of these applications you're most interested in, and we can kind of think about how the Boresight calibration ties in with your particular application. So of course, there are so many different things that you can do with LiDAR surveying. It's hard to capture them all. So we've given these 5 different answers here. We've got asset management, digital mapping, infrastructure monitoring, geographic surveys, and other. So other might be, say, autonomous vehicles, or whatever your other application might be. Okay, thank you everybody. I'll try to tie that in with the presentation as we go along. So, we are Oxford Technical Solutions, as many of you will know, and we have over 20 years of experience in getting the best navigation data out of our iconic red box INS devices. So we also have a webinar on why you need an INS device to pair with a LiDAR if you're doing a LiDAR survey. But you probably know that you need to pair the INS with a LiDAR in order to give orientation and the best position, navigation data and diagnostics to the LiDAR. So we've been doing this for a long time before LiDAR surveying became a thing, and we are now the only INS manufacturer to provide a Boresight calibration solution. So, what is it? So the problem is Boresight misalignment, and essentially that comes from having an imprecision in the angles that you measure between your LiDAR and your INS. So you'll probably know that if you're trying to georeference a point cloud with some navigation device and a LiDAR, you'll need to know exactly the distance away from the INS that the LiDAR is at along 3 axes, and also the angles. And when you don't know those angles super precisely, you can get a distortion in your point cloud. So when I say super precise, we will have some examples later on, and you'll see that it needs to be about 0.1 degrees for the best precision. So this is exactly like some gun sights. So if you've got a sight on a gun and you have to boresight the barrel of the gun so that they match up. And a thing to note is that the further away from the device you are surveying, the more pronounced this problem gets, and we'll see that again later. So the reason it is a problem is because if you're trying to survey a object, say this black rectangle, and you have this misalignment, and of course you will always have a misalignment to some extent, you can't get perfect precision. If you have, say, an exaggerated misalignment, then you might see the black rectangle as the red rectangle. It will be distorted and it will be displaced from what it should be. And then if you view that same object from a different perspective, say if you turned around and you were viewing it from the other direction, you would have, again, a distortion and a displacement, but it will be in a different direction. And so in your point cloud, you're going to get these different profiles of the same object overlapping with each other. And so instead of a nice crisp rectangle like you see here, you start to get overlapping blurred images until the final point cloud is blurred itself. And it can be very difficult for many applications, particularly intelligent classification, or just measuring distances or measuring volumes, for example, if you've got this kind of distortion in your point cloud. So as a quick calculation, you can expect about a 10 centimeter displacement in any points that you see 15 meters away if you have an error of just half a degree in one of the axes. So that is, of course, quite significant. And if you imagine you are driving one way and you see this 10 centimeter displacement, and then you turn around and you survey the same object, that's going to be a 20 centimeter displacement for objects just 15 meters away. So in practice, this is a very real effect, and you need to consider it in any LiDAR surveying that you do. The further away you are hoping to survey, the more pronounced this effect will be. And you can get, in the worst case, a double vision. So if you imagine, if I go back, if you imagine this red and this blue rectangle, if the case is so bad that the Boresight misalignment is large enough, these two profiles that you're seeing of the same object can not overlap, and they'll actually be separate, and you'll see two of the same object. So instead of blurring, although there will be distortion, you also get two of the same object. And you need to have about 0.1 degree precision in your axes for this to not be the case. And this is essentially impossible for by eye methods or other physical measuring devices. So you really need a data-driven calibration technique, which is what we have. You could also do it with a CAD mount. So if you mapped out your CAD model on your PC before printing it, you might be able to get the precision that you need. That is, of course, very time-consuming. It can be very expensive and doesn't give you a flexible solution at the end. So our solution, OxTS Boresight calibration. So these are some examples of data. So what you're seeing here is a point cloud that has been filtered for only the highly reflective objects. So you should be able to see 4 squares. Now what these are actually 2 squares in real life, but you can see 4 of them because double vision has occurred. So what has happened is a UAV has flown over 2 targets going north. It has then turned around and flown south over the same targets. And as you saw before with the red and the blue rectangle, what's happened here is the 2 profiles of this object that it's seen have not overlapped at all, and we've got 2 instances of the same object. But if we boresight this, you can see that we have 2 objects as we should, and they are crisper, they are more square, and they're denser as they should be. And that's really the aim of what we're getting at. So this is actually the same data, but the whole point cloud, not just reflective points. So you can see the target still. There are a few more passes, so not just north and south, but a whole range of movement. And you can see that this point cloud is very blurry. and almost unusable. You can make out some different things. Say you might be able to make out a car and a van if you knew it was there, but you can almost see 3 of the same car, you can almost see 2 of the same van, and so it's really not usable, and you wouldn't want to give a customer a point cloud that looks like this. But after boresighting, you can see a very clear car, a very clear van, you can see all the different features of the landscape that have been surveyed. So here's some more examples. So this is on a land vehicle. We have driven north, that's in the blue, and we've driven south. So we've turned around and come back south, and that's in the red. And you can see that there is this displacement between the red and the blue, and you can see very clearly that it gets greater, almost a linear relationship, the further away from the car that the points are. So if we now boresight this data, you can see that they overlap as they should, and there's no divergence as the points get further away. So you can survey the same objects, again, adding to your point cloud instead of ruining your point cloud. Here's another example. So what you're seeing here are, on the left, you've got a north pass and a south path. And you can see obviously that there is a displacement between the two, and you've got double vision again. This often happens with small objects. So the cross section of a lamppost is quite small, so you're probably going to see 2 of the same object there if you don't have that boresighted. And on the right, you can see the boresighted solution with the point cloud aligning perfectly. And so if you thought that you could get away with not caring about relative displacements, so say you don't want to survey the same object twice, you'll just do it once, but you do care about the absolute position of objects in the world, then you still need to boresight. As you can see here, there's about a meter difference between this boresighted solution, which would be the reference, and the non-boresighted. So if you're surveying objects some tens of meters away, they're going to be in the wrong position by some meters. And that's obviously, if you're caring about absolute accuracy, something you want to account for. So the procedure is very simple. You mount your LiDAR and your INS together. You measure the displacements and the angles between the two. You set up these targets that we have. These are very simple retroreflective targets, so you can get this tape on Amazon and just cover a board, for example. And then you drive around or fly around and have your LiDAR view the targets from a range of angles and distances. And then you let the software do the hard work for you, and that will give you a boresighted solution. So you measure the angles to the best of your ability, and then the software will calibrate that to 0.1 degrees. So we're going to go through an example now. So what you can see here, these are 2 point clouds filtered for only the reflective points again. And one of these is boresighted and one is not. So we can see 2 targets, that's in the green, and you can see these strips. So these are strips on our airfield. These are reflective strips that they just have. So if I zoom in, you can see it's a bit of a mess for the unboresighted solution. So this is unboresighted. The targets are kind of smeared out. There's about a meter displacement. And these strips on our airfield are, you can see 2 instances. So there's double vision going on there. So if I now turn on the boresighted solution, turn off the unboresighted, you can see a nice square target, as we should have. And these strips, we do not see double vision. So we've got nice square targets as we should. So this is our Georeferencer software. And I'll show you now how the boresighting process is done. So we drag in the relevant files. So what we have is an NCOM file, which is just the navigation data from our INS. We have a VAT file, which is another INS file that you just get with the data. We've got a LiDAR file, so that would be your PCAP, for example. And then we've got these two files, which are the displacements and the angles between the INS and the LiDAR. So for example, this is 78 centimeters in the x-axis, etc. So I'll show you that in a second. And you can see on the right here, this is where we've been driving around on our airfield. So we've got a target, I think, here and a target here. And we've just driven around trying to get the LiDAR to see the targets from different angles and different ranges. So if we now have a look at the hardware tab, you can see what we had was a INS device in the boot or the trunk of the car. And then mounted on the back window of the car is the LiDAR device. And we can change these X, Y, Z values and the different angles. So what we did was we tried to measure the angles as accurately as possible just using our eyes. And we got 90, 0, and 55 on the 3 axes. And the 55 was quite difficult to get, as you can imagine. So if we now click Run Boresight Calibration, so the total amount that the user has to tell the software is very small. So what it's doing now is it's screening the point cloud data for only the retroreflective points. And then it's going to make a prediction of where it thinks the targets are. Okay, so usually the software will get this right. It will tell you where the targets are exactly. But we have these reflective strips on our airfield, which is quite a rare case. And so we have to tell the software ourselves. So if we say it's here and here, as we can tell that they are. And the important thing is just to make sure that there are no other retroreflective objects within this search radius. And we can change the diameter of that search radius. So if we just choose what altitudes these are at, and then check the target point, so it counts the number of points on each one of these targets. And then we continue Boresight. And that is it as far as the user is concerned. So this graph on the left here can be useful. So this tells you the angles and distances at which the LiDAR scored hits on the boresighting targets. So you can see this range of 100 degrees here. This is where the LiDAR mounted on the back of the window, that's viewing the sky essentially. And at the 180 degrees before that, it's essentially viewing the ground here. So that is the boresight process complete. So you can see the before and after angles. So we've got 90, it changed it to 88.728. 0 has changed by minus half a degrees, and the roll has changed about 0.2 of degrees. And this is the data that you saw here. So that 1.2 degrees difference, it might sound small, and it is, especially to our eyes, but to a point cloud, it's actually quite significant. So you can get large distortions just from that 1.2 degrees. And that is considering that that is the best that we could do with our eyes. and even getting the 55 is quite difficult. So getting within one or 2 degrees is about all you can do, and you need to really get 0.1 degrees for the best data, where your inaccuracies are coming in then just from the LiDAR device itself or the INS inaccuracies. So that is our Boresight calibration solution. And I'd just like to ask you a second poll question now. So at what kind of distances are you likely to survey objects from? So remember, this is important because there's almost a linear relationship between the distance at which you want to survey from and the inaccuracy of your points in your point cloud from the Boresight calibration. And if you remember the point cloud that we just saw with the targets, that distortion which smeared out the target quite significantly, that was viewing the target from, I think, a maximum of about 15 meters. So that might give you an idea of how significant this problem can be. Okay, thank you, everybody. Yeah, so a wide range of distances. Okay, so summary. So the Boresight misalignment causes blurring and double vision that can make many applications such as intelligent classification, whether you're using algorithms particularly, or you're doing it by eye, or you're trying to measure distances, or you're trying to count objects, or count or measure densities, trying to measure volumes. All of these things, for quite obvious reasons, can become very difficult. You're obviously going to lose any fine details. So if you want to give a customer a pitch, for example, for why they should choose you, you want to give them the best looking point clouds that can be used very easily for different applications. You're going to need to Boresight your data. Remember that the further away objects are, the more significant this is, and that a data-driven calibration technique is essentially necessary for you to get the precision that you need. And I would just say that the Boresight solution procedure that we have with the targets, this can be done in a couple of minutes. It can be added onto any survey run. You can even use the same file. So it's very convenient, and it really gives you the confidence to just go out and survey. You don't need a huge amount of planning. You don't need CAD models. You don't need all of this. You can be very flexible and very confident that you're going to get the precision that you want. So these slides and this recording should go out to you at some point, and you can access the links if you want to contact us. Do get in touch. If you want to ask a question, you can ask it in the chat there, but also you can email us. You can find a lot on our website. So we have some time for questions now.
Yeah, thanks, Jake. Again, if you have any questions, then please type them in the questions chat box. So first question we've got is, do you have to calibrate your Boresight on the LiDAR equipment every time you want to operate it, or just once?
So this depends if you want to use the same configuration. So if you if you don't move the LiDAR and the INS relative to each other, if you just keep them in the vehicle exactly as they are, then you only need to do it once. But of course, if you wanted to change the setup, then you're going to have to calibrate that new setup. So what you're doing with this calibration is you're calibrating the setup. So the angles between the INS and the LiDAR. So if you change either of those, then of course you're going to have to boresight again. But you should only need to do it once if you make sure that you're keeping them very tightly coupled together. So if you move them more than 0.1 degrees relative to each other, then you probably need to boresight again.
Okay, thanks, Jake. So that's the only question that we've got at the minute. We still have a few minutes, so again, if you have any questions, that's the time to ask it. In the meantime, as we wait, I'm just wanted to remind you that we have another webinar running this week that you might be interested in. That's a webinar on point cloud accuracy and the factors that can affect it. That will be running twice, next Friday at 9:15 and 3:15 p.m. British Summer Time. So if you are interested or know anyone that could be interested, please let them know and do join us. We also, like Jake mentioned, we've been running a number of webinars this month, so you can find the recordings on our website if interested, on a number of topics, many of them definitely related to surveying. Okay, another question that we've got, how many LiDAR suppliers are supported at the moment?
So at the moment, only Velodyne is supported, so the VLP-16. We are currently already working towards getting all of the Velodyne units, all of the Ouster units, SI units, and some others we're looking into as well. So we're hoping to have those later on in this year.
Yeah, the best part of this development, I can confirm. We will start with integrating the rest of Velodyne models, and then we will move next to Ouster and Hesai, and we will aim to get the best part of this development done by the end of this year. Okay, next question is, what kind of format do you use? Not sure exactly format of what. Is that the LiDAR data or the INS data? So I can take this, Jake, if you are fine. So if it's the LiDAR data, we can use both PCAP. That's available as a standard with most LiDARs, but we also have a proprietary format, which is the LCOM. So we can get this other second format if you enable a feature code on our devices, but PCAP is perfectly fine. As for the INS data, then our software would only work with our own proprietary format. That's the NCOM file that you can get out of the OxTS INS units. Over to you, Jake, if you want to add anything on this.
No, I think you covered it quite well. Yeah, you can just use the standard PCAP data capture for the LiDAR.
Okay. How big can the LiDAR data be?
I would say that depends on your computer. I don't think the software has any limitations.
Yeah, does it depend on the points? The next question. Well, yes, obviously it will depend on a number of factors. So obviously how long the logging is, what sort of RPM you have used. Higher RPM can give you more point density, depending how your targets are positioned relative to the LiDAR. So the way you hit them, it will depend also on. So regardless on the size of the LiDAR file that you have, you can apply using our software some filters. So you can only make the software take into consideration just points that have a reflectivity threshold that is high enough. So you can filter your data based on reflectivity threshold. You can filter based on distance. So you consider only objects that are within, say, 15 or 20 or 50, whatever. So you can filter the data, and basically by doing this, effectively bring the amount of data that the software has to process and the resulting point cloud, bring that size down. But like Jake said, it pretty much depends on how performing your PC, your laptop would be in handling big files.
Mm-hmm.
Okay, anything else? If not, then I guess, sorry, we've got another question. Is it GPU or CPU? Well, I would say for the processing, that would be CPU. And then when you have to open the point cloud and, you know, a software like Cloud Compare or something, then the GPU would come into it. What would you say, Jake?
Yeah.
Yeah, processing itself.
That's what he's asking. Yeah.
Yeah, processing. I think that's the question. Processing itself. So using OxTS Georeferencer has nothing to do with the graphics. You know, it's just pure processing power. When you display the point cloud, obviously, you know, the graphics capacity on your laptop would come into play. Is parallel computing used? Again, that depends on what laptop you are using. So the software will be running using whatever resources it has available on a given PC.
Mm-hmm.
But you know, this is not extremely relevant, put it this way. Okay, if this is it, I guess we can terminate our webinar here. Thank you everyone for joining. Thanks, Jake, and have a good day.
Yep. Thank you, everybody.